Hi everyone, my name is Rodrigo, and in this talk I'll present our new function merging technique where we address a key limitation from our previous work. By handling SSA form, including file nodes, we eliminate the need to perform register demotion, improving our capability of merging functions. In this work, our focus is on code compression. Optimizations that reduce code size are important for resource-constrained devices, for example in embedded systems. A key optimization for code size reduction is function merging. For those not familiar with this optimization, a very simple analogy would be the spork, which combines the functionality of a spoon and a fork in a single item. Function merging does something similar to functions in a program, with the difference that, unlike sporks, this is one people actually enjoy and use. In our case, we want to replace different functions in a program by a single one that can perform all their tasks. The most trivial way of doing that is to encapsulate two functions entirely underneath else, where we select which function to execute depending on a parameter. However, this would not result in code size reduction, as we are only adding extra code. A better way of doing that is to identify as much similarity as possible in order to reuse the same code for both functions, having only that difference under if-else constructions, thereby reducing code size. In our previous work, we have proposed to use sequence alignments to identify where two functions are similar and where they are different. In order to apply sequence alignments to a pair of functions, we convert their control flow graphs to linearized sequences. After alignment, code is generated directly from the aligned sequences, where the control flow graph of the merged function is finally created. This code generator works on aligned sequences one instruction at a time without revisiting the original control flow graphs. Because the aligned sequence has little information from the control flow graph, it was required that register demotion had been performed to replace SSA file nodes with memory operations. This was necessary because memory operations can be processed in isolation, while file nodes require edge information from the control flow. Register demotion is applied hoping that it will be reversed later by register promotion. However, that's not always the case. And as we'll see next, it comes at a cost. Our proposed approach solves this limitation by fully handling the SSA form and its file nodes. The most obvious negative impact from register demotion is code size increase. Every file node is replaced by 4 or more memory operations. To remove the file node in this example, first we need to allocate some memory, then each incoming edge of the file node will essentially become a store instruction. Finally, we need to load the value from memory in the place where we had a file node. Overall, this function is almost doubled in size. Although this is only a small example to illustrate this impact, we also see a similar trend in full benchmarks. For example, in the Spec 2006 benchmark suite, register demotion increases function size by almost twice on average if you look at the number of instructions in the LLVM code. Although we have an inverse transformation called register promotion, or mem2reg, depending on how we change the code by merging two functions, it's often not possible to reverse the impact of register demotion. For example, if we merge these instructions, we'll see that the corresponding load instruction from each function is using a different address. Function 1 is loading from the first allocated address, while function 2 is loading from the second. As a result, the merge load instruction will need to select which address to use, depending on the function identifier. Because of this poor alignment regarding these memory operations, the address manipulation becomes complex enough that reversing these instructions to file node is infeasible. Even in this simple example, we can end up paying the full price of using register demotion before function merging. Now we'll describe our approach called SalSSA, which stands for Sequence Alignment in SSA. SalSSA has a pipeline similar to our previous approach. Without the need for register demotion, we first linearize the control flow graphs for sequence alignment. Then we extend the original control flow graphs with the alignment information. Our goal during code generation is to essentially clone the original functions, but whenever we have a pair of aligned instructions, we jump to a unified point. Let's see how SalSSA works in this small example. We'll focus on the code generation. For that, let's assume we have the sequence alignment shown here. Note that we ignore the file nodes during sequence alignment. We do that because they have a special treatment later. Note also that SalSSA differs from our previous work by combining the result from the sequence alignment with the original control flow graphs. At this point, we start by first generating all merged instructions and labels, each one in a basic block of its own. So from the beginning, these two matching labels will go into their own merged basic block. Then, the two call instructions are merged into a separate basic block. And we do the same for every matching pair of instructions or labels. Once we have all merged instructions in individual basic blocks, we go through each control flow graph, cloning the remaining non-matching instructions or labels. During this process, we also connect the merged blocks following the correct order for each function. If necessary, we add a conditional branch instruction to split the control flow according to the correct execution path in each function. File nodes are simply copied into its appropriate basic block. If the basic block has a matching label, the file nodes are copied into the merged basic block for that label. Once we have fully generated the merged control flow graph, we resolve the operands. The trivial case is when two merged instructions have the same operand, where we just keep it as is. But whenever a merged instruction has different operands in each function, we need to add a new instruction to select a correct operand accordingly, as shown here. Similar to the previous technique, we also optimize commutative operations in order to minimize the number of selections needed. For example, in this addition, instead of simply selecting both operands, to reduce code size, we can first reorder the operands, maximizing the number of matching operands. Finally, we'll need a single select instruction. Labels need a special handling. If a merged instruction has different label operands, then we create a new basic block with a conditional branch to the appropriate pair of labels. We can also optimize a special case of a conditional branch instruction. Even though this instruction is not commutative, we can swap the operands from function 1 by applying an XOR operation to the condition and the Boolean function identifier. The XOR operation will swap the condition for function 1, therefore allowing us to also swap the label operands. Once we have resolved the operands, we might end up with some trivial jumps that we can simply eliminate. As mentioned before, our main focus is on code size reduction. For our evaluation, we compile the Spec 2006 benchmark suite using link time optimization for size. In this evaluation, we achieved twice as much reduction as our previous work. This is a very significant improvement considering that the code was already highly optimized. This improvement comes from our capability to produce much better merged code while also operating on small sequences. This figure shows how we are able to achieve a greater code reduction. Here, we show the average number of profitable merge operations. By being able to natively handle the SSA form, SalSSA generates better merged functions, resulting in more profitable merge operations overall, which translates directly into more code size reduction. SalSSA also has a much smaller compilation overhead than our previous technique. Because the sequence alignment algorithm is quadratic in time and space, reducing the average size of sequences by almost half is very beneficial for both compilation time and memory usage. And that impact is what we're observing in this evaluation. In this figure, we show an important breakdown of how SalSSA compares to the previous technique. In particular, it shows SalSSA's speedup relative to the sequence alignment and code generation. These measurements represent the average aggregate time. As you can see, SalSSA achieves a significant speedup. This is a direct result from working with smaller sequences. As mentioned before, registered motion tends to almost double the size of a function. Since sequence alignment has a quadratic time complexity, SalSSA ends up being over 3 times faster during sequence alignment. Meanwhile, the code generator is sped up by a factor of almost 1.7, which is expected due to its linear time complexity. So, to conclude, we have described our new function merging technique called SalSSA, which is able to effectively and fully handle the SSA form, including phi nodes. By avoiding registered motion, SalSSA works on smaller sequences, reducing compilation time, while also producing much better merged functions. And this results in about twice as much code size reduction compared to our previous technique. For more detail, please look at our paper. And thanks everyone for watching to the end. Bye!